In a previous video, we showed that there was a natural transformation going from the identity functor on the category of vector spaces over a fixed field K and our double dual functor that we defined. So shortly here I'm going to recall the definition of the double dual functor, but the purpose of this video is to wonder what would happen if we instead looked at a mapping from V into V star, the single dual space of V. So we showed that there's a natural transformation when you go from the vector space to its double dual, but what happens when you go from a vector space to a single dual? Is there a natural transformation or is there no natural transformation? First, let's start by recalling the definition of the double dual functor. So recall that the dual of a vector space V, V star, is the set of all linear functionals defined on V, that is, all the linear transformations going from V into its underlying field K. And we said that we know that V star forms a vector space over K in its own right, and that therefore V star belongs to vect K. But if V star belongs to vect K, then V double star must also belong to vect K because it's just the dual of a vector space in vect K. Therefore, we know that V star star, V star, and V are all vector spaces in vect K. Next, let's recall the definition of precede by T. So if T is a linear transformation going from V into W, then we can define precede by T, which takes in a linear functional on W in W star, and simply moves T in front of it, just precedes this linear functional by T. So that gives us F after T. And what is F after T? Well, T goes from V into W, and F goes from W into K. So F after T goes from V into K. That is a linear functional on V. We found out that precede by T is actually a linear transformation, since W star is a vector space over K and V star is a vector space over K. We found out that this is actually a linear transformation in vect K, and therefore we can apply double precede by. So we can just take a linear transformation precede by T and apply precede by to it. And this will go from V double star to W double star, defined by T double precede by applied to F is F after T precede by. So you move it in front once, but there's still a precede by remaining there. And so we said that the double dual functor D sends a vector space V into its double dual space V star star, and sends a linear transformation T into its double precede by version, T double precede by. And when we define D in this way, we find that we get a natural transformation, lambda, going from the identity functor, defined on vect K, into this functor D that we've defined. And so in order to get that, we need this equation to hold, double precede by T after lambda V, so the component of lambda for the vector space V equals the component for W after T. And that's just showing that this square here commutes, which guarantees that we have a natural transformation. And we said that the components were defined by these evaluate for functions, or eval for functions, and those took vectors in our vector space V and gave us back a function eval at V. So it was important not to confuse eval for and eval at. Eval at simply just takes the linear functional and applies it to V, f of V here, whereas eval for V gives us the function back that is defined in this way. So the question we wanted to ask ourselves was, if D sends a vector space V to its double dual space, and sends a linear transformation t to double precede by t, then is there a natural transformation if we just do the single version of this? That is, maybe we define some s where s of v is just v star and s of t is just single precede by t. So if you want, pause the video here and ask yourselves, is there some lambda prime which is a natural transformation going from the identity functor on vect k into our newly defined single-dual functor s? If you want a quick hint, I'll tell you that the answer is no. There is no natural transformation which goes from the identity functor into this hypothetical functor s. Remember, we haven't proved that s is actually a well-defined functor, but we're just asking if it were, would there be a natural transformation? And the answer is no. So if you want a hint, now you can pause the video here and try to figure out why is there not a natural transformation that looks like this. Well, the answer is actually pretty straightforward. If you're going to apply precede by t, where t goes from v to w, to a linear functional f, well, then you're going to get f after t, and t goes from v to w, so the domain of f has to be w. That has to be a linear functional defined in w star, not in v star. So what is the problem? Well, t goes from v into w, but the image under s, which is precede by t, goes from w star into v star. And so s would have to be a contravariant functor. So of course, there's no natural transformation from a covariant functor, like the identity functor, into a contravariant functor like s. So is that the end of the story? Do we have to just give up and say, well, the definition of s is contravariant and the definition of the identity functor is covariant, so we'll never be able to have this commutativity property that we need, and so there will never be a natural transformation between the identity functor and s? Or could we maybe somehow tweak this definition of s so that this does become a covariant functor again instead, so that at least it has a chance, at least it lines up in this square pattern so that we can investigate it to see whether or not there's some potential natural transformation between the two? Well, what if our natural transformation t had an inverse? Well, if t has an inverse, then the inverse goes from w back to v. And if we use this definition but instead apply precede by the inverse and apply that to a linear functional f, we get f after t inverse. And since t inverse goes from w into v, well, f has to go from v into k, which means that this goes from a linear functional in v star to a linear functional that goes from w to v and v to k, that is w to k, which is w star. So we have that this definition would line up. If we replace this with precede by the inverse, then this would allow us to define a covariant functor as long as we checked that it was actually a well-defined functor. So we'd like to define our functor s in this way. However, there's still one outstanding problem, which is that we just assumed that t had an inverse, which of course is not going to be true for all of the linear transformations in vect k. there are going to be certain linear transformations which are not invertible, and so they won't have an image because we won't be able to find this T inverse. So what can we do to rectify that problem? Well, we can restrict ourselves to, instead of any vector space, let's use only vector spaces where we know we're going to have an inverse. So let's take instead the category of finite dimensional real inner product spaces. This category is called fine inner, where the objects are, of course, finite dimensional real inner product spaces, so a subset of all the vector spaces that we were looking at before, and where we've fixed the field K to be the real numbers. And the morphisms are, while we want morphisms that are linear transformations that preserve inner products, right? Because this is specifically looking at inner product spaces, so we want morphisms that are going to preserve those inner products. So we call these unitary transformations. And unitary transformations are simply linear bijections that preserve inner products. That is, if U is a unitary transformation from V to W, then the inner product of the images of V1 and V2 under U in W has to be equal to the inner product of V1 and V2 in V, right? It preserves the inner product when you map it by this unitary transformation U. Thanks to this restriction, going from arbitrary vector spaces to only finite dimensional real inner product spaces, and going from arbitrary linear transformations to unitary transformations, we see that all of the transformations are bijections, and so every transformation in this category has an inverse. And so the only thing we would need to prove there is that the inverse of a unitary transformation is also a unitary transformation. So you can try that as an exercise, should be pretty quick. And so what we can say is that maybe we actually can define this functor that we wanted to define before on this category instead of just vect k, because we showed that vect k wouldn't work because the inverses might not exist. So let's try it for this new category that we've mentioned. First, identities map to identities, because if I apply S to the identity transformation on V, then I get the identity transformation on V inverse and precede by. But of course, the identity transformation inverse is just the identity transformation. So this is just precede by the identity transformation on V. And this is the identity on V star. So if you don't believe me, check that. But this is the identity transformation on V star. And so we're good. It does preserve identities. Next, if we apply S to U1 after U2, where U2 goes from V to W and U1 goes from W to Z, and we apply that to a linear functional f going from V into the real numbers. Then we get that this is equal to precede by the inverse of u1 after u2. Applied to f, which is equal to applying precede by, so f after the inverse of u1 after u2, which is equal to, well, we can break up the inverse and say f after the inverse of u1, but we have to flip the order because it's inverted, so u2 inverse, u1 inverse, which is equal to, well, this is precede by the inverse of u2, so we can just move that in front to get precede by the inverse of u2 applied to f after the inverse of u1. But this is just precede by the inverse of u1 applied to all of this. So that's the inverse of u1 precede by applied to precede by the inverse of u2 applied to f. But this is just s of u1 after s of u2 all applied to f. And so what does that give us from beginning to end? We get that s of u1 after u2 is equal to s of u1 after s of u2. And so that satisfies the second definition, or the second condition for the definition of a functor. So we're good. This single dual functor that we've defined, now that we've restricted ourselves to this category, is actually a well-defined functor. So the next question is there a natural transformation from the identity to this functor, S? And so in order to do that, let's update our diagram and our commutativity property up here. So these functors now go from fine inner to fine inner instead of vect k to vect k. This is now no longer D. This is not the double dual, but the single dual, S. What that means is that this V does not get mapped to V double star, but gets mapped to V star. And same with W. And this is now no longer an arbitrary linear transformation, but a unitary transformation. So let's call it U. And this is U as well, because this is just the identity functor. And this now is no longer double precede by. Instead, it's precede by the inverse of U. And so now this natural transformation that we're trying to find, we don't know if it exists, goes now not from I to D, but from I to S. And same here, we need to replace this with the inverse of U precede by, and this needs to change to be u. So this is the updated condition for a natural transformation from the identity functor on the finite dimensional real inner product spaces to the single dual functor that we just defined. In this case, there actually is a natural transformation going from the identity functor to our single dual functor S, and it corresponds to taking each component, lambda v, to be equal to the Riesz map on v, which is a mapping from v into v star, defined by basically take the inner product with v. So rv of a vector v is just equal to take the inner product with v, which is in the linear functionals on v, because it takes in another vector, say x, and then returns the inner product here, which is going to be a scalar in the real numbers. So this is a mapping that goes from the vector space v, which, remember, in this case is a specific finite dimensional real inner product space, and brings you to the dual of that space. In order to prove that this is a natural transformation, we need to establish this equation. And so let's take the left-hand side. We get that precede by the inverse of u after the Riesz map on v, and then apply this to some vector v and v. Well, this is going to be equal to just applying the composition here. This is precede by the inverse of u applied to rv of v. And then this, if we apply the precede by, is going to be rv of v after the inverse of u. But this is take the inner product with v, the linear functional, after the inverse of u, which is equal to take the inner product with v of the inverse of u of the vector that you're talking about, effectively. And then because these maps, unitary maps, preserve inner products, we can actually apply u on both sides to get that this is equal to u of v after u of u inverse applied to the vector that you want, which is equal to simply take the inner product with u of v. But this is equal to the Riesz map on w of u of v. Right? That's just the definition of the Riesz map. And so this can be broken out into a composition. So the Riesz map after u applied to v. And if that's the case, then we have established that the inverse of u precede by after rv, the Riesz map on v, is equal to the Riesz map on w after u. But why is that important? Well, that is exactly what we needed to show up here. So we've established that there is, in fact, a natural transformation from the identity functor to the single dual functor if you restrict yourself to finite dimensional real inner product spaces. We saw it failed for general vector spaces, but in this case, it will satisfy the definition if you make this restriction. So this is a pretty interesting aside to the double dual space. And there's a theorem called the Riesz representation theorem, which actually proves, if you look into it, that not only is this a natural transformation, but it's actually a natural isomorphism. So what we can establish is that we actually have a natural isomorphism between the two. So that's QED.